Hello, I'm going to help you with this hemophilia worksheet if you're needing some help. So I wanted to go over a little bit about sex-linked traits so that you can figure this out a little easier. Hopefully you remember that if you have an XY, that makes you a male, and if you're XX, that makes you a female. And so some genes are found on our autosomes, our first 22 pairs of chromosomes, but sometimes genes are found on our sex chromosomes, our X or Y, and in particular our X chromosome. So when a gene is on our X or Y chromosome, we call them sex-linked traits because they're linked to the sex chromosome. And we're usually talking about the X chromosome because both males and females have X chromosomes. So these are some various sex-linked traits. And I'm going to show you kind of how they're carried. So a woman has two X's, and she can have two normal X's and be normal. But if she has, let's say she has one of the genes for one of the diseases, like a hemophilia gene, which is on the X chromosome. But as long as she has a regular X chromosome that's normal, then she's going to be normal because this is actually a recessive gene, so it's going to hide. So it should not be capital. If she gets a color blindness gene on one of her X chromosomes, that's still fine because she has a normal colorblind gene, non-colorblind gene. So she's going to be able to see color. And same thing, I'm not sure what this is, balding. If she has a balding gene on one of her X chromosomes, she's okay. So all of these can result in a female who still is normal. But a male only has one X chromosome. So if his X chromosome has that affected gene, like hemophilia or color blindness or male pattern balding, then he is going to have that trait because he has no other X chromosome to be dominant. So because he only has one X chromosome, whatever that X chromosome is, that's what is going to display in his traits. It can't hide anywhere. It can't be recessive and hide. So that's what happens to the man. And so here's an example of how it can be passed on. So here is the male pattern the baldness gene. It's on an X chromosome. So the woman is carrying it. And she's not bald because she has another X chromosome, but she's carrying it. And the man has a regular X, so he's okay. But you can see that if these are the woman's chromosomes, she can give either the balding gene X or the normal gene X, and he's giving either a normal X or a normal Y. So if both of them give a normal X, they're fine. If she gives a normal X and he gives normal Y, fine. If she gives the balding gene X, but he gives the normal X, then their daughter will be fine. She'll be a carrier. But if he gives his Y and she gives the balding X, then their son is going to be bald. So you can see how there's a greater chance that the son is going to have one of these sex-linked traits because he only has one X chromosome. It's a lot harder for a woman to have both of her X's be affected. It can happen, but it's much more rare. It's much more common for the son to have one of these sex-linked traits. So here it is. She can pass this to her offspring, and in particular, her son, but she's just a carrier. Okay, women can be bald too, but they have to get two of those X chromosomes. So the way a woman can get it is if her father already has that gene and her mother is a carrier. Okay, so I'm going to jump over to this hemophilia pedigree. So here is Queen Victoria, and this is actually a really amazing pedigree. If you want to know more in detail, I mean, you can see everyone's names, including Prince William, Prince Kate, Prince Harry, who didn't, this is not updated with his new wife and kids, but here is all the different royal families that came off of Queen Victoria and all her kids and who they married. So if you look on this one, it shows like this is Russian royalty, and actually one of these children are Anastasia from that Disney movie, Anastasia. Not that she's from the Disney movie, but Disney made a movie about her. Here's the Spanish royalty. They married into the Spanish royalty, German, and current English royalty. So it's a pretty impressive family tree, but let's go ahead and take a look at what these squares and circles mean. So the circles are female and the squares are male. The circles, if it's half filled in, then that means that is a woman carrier. And I don't know if it shows here. I couldn't get this over here, but half filled is a carrier female. Males cannot be carriers because they only have one X. So they either have it or they don't have it. And a normal female will be an open circle. So you can see that it looks like it started with Queen Victoria and her husband. So Queen Victoria was the one that actually had the hemophilia gene. So any female she had, she could have given her regular X or X with the hemophilia gene, but you can see here is her son who has hemophilia, and you can see that he must have gotten the hemophilia gene, the X with the H, from his mom. She was a carrier, but you can see that she must have given that X with the hemophilia gene to her two sons, and she also gave the X to her daughter. And the reason why we know that is because her two sons have hemophilia. Here, he has hemophilia, and he gave it to his daughter, and his daughter gave it to her son. And then it looks like it kind of stopped here. Here with Queen Victoria, she gave it to her daughter Alice, who was a carrier. So she gave one X with the hemophilia gene, who gave it to this daughter. And the reason why we know this daughter has it is because two of her sons had hemophilia. She also gave it to her son, and then she gave it to this daughter, who ended up having a son with hemophilia. So hopefully that helps you understand the passing on. I was going to try and write a Punnett square, but I don't think I can do that with my text box. But hopefully you can see, if you're going to do any Punnett squares, you can do it this way. So if one of the, like Queen Victoria, this would be her, except for instead of the B, you would put an H for hemophilia. And she married Albert. And so you can see that her son would be an X with an HY, and then her daughter, who's a carrier, would be X with an X and an H. And then you can see, for instance, if her, it looks like all of them were carrier daughters with normal married to men with normal X's, but then the mom is the one that passed it on to her son. So that's what happened there. Okay, so hopefully you can figure that out. If you want to do some of these questions, I would love for you to give them a try. You don't have to do all of them. There's a lot, but I just wanted you to get a feel for one of these real life stories of how hemophilia is passed on and how it uses a sex link gene to pass along.